found to be 30 centimeters with a possible error in measurement of 0.1. Use differentials to estimate the maximum possible error, relative error, and percentage error in computing the volume of the cube as well as the surface area of the cube. So this is 33 on page 255. Ready? So we read it one more time. It says the edge of a cube. So here's the cube. X, 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 and so on and so forth. So it was found to be 30 centimeters with a possible error in the measurement of 0.1 centimeter. So 8. What is this? Perfect. What is this? Perfect. Perfect. So now it says find, using differentials, estimate the maximum possible error in the volume. So that's the first thing. And in the surface area. So we're asked to estimate. So are we using delta V and delta S, or are we using dV and ds? Right, because it's the estimate, of course. Good. So can anyone give us the volume of the cube?
X cubed.
Perfect. And the surface area of the cube?
6x.
Squared. Perfect. Can anyone now give us dV? Remember, it's not the derivative, but the differential. Excellent. Can anyone give us ds? Excellent. I have all the information. I can go ahead and put them in. 3 times 30 squared times 0.1. 12 times 30 times 0.1. The measurement unit, when you give me the number, the measurement unit for the first one is? Excellent. And the other one? Perfect. We have the numbers? Or I'll calculate them. Now we want the relative error for the volume and the relative error for the surface area. Yes? Okay, so yes.
Is
Greg?
the v equals x cubed and s equals 6x squared, are those formulas for it, or
Yes. So the volume of a cube is the area of the base times the height. So x squared times x. And the cube has 6 identical faces.
okay,
And x times 6.
okay.
Okay, so do we have these numbers? So this is 927, so 270, and then 30, this is 360, 36. Okay, perfect. I got it. So what is the relative error for the volume? How do I determine it? Remember, it's error over the original. Good. So dV is 3x squared dx, and v is x cubed. Nice. 3 times the relative error of the edge, and the other one is ds over s, or 12x dx over 6x squared twice. So a 0.1 change in the edge of the cube triggers 3 times as much related error of the error in edge and the edge of the cube, and the surface twice as much. And yes, we can determine them because we're asked to do that. So this is 3 times 0.1 over 30, and the other one is 2 times 0.1 over 30. And these numbers have to be determined, and also we have to change them into percent. So this is 0.01, which is 1%, and this is 0.1 over 15. 2 zeros, right? Okay, so this will be 0.67%. So 1% error in the volume and 0.67% in the area. Any questions? Okay, I would like us to look at, yes, Greg?
That's surface area, right? 0.67.
Yes, that's for the second one.
Okay.
And that's the first one is right here.
Okay.
1% for the volume.
Gotcha.
Okay, so let's look at a function and determine the delta y and dy for any function you want. And then we can look at linear approximations. Okay, so let's look at 19. 19 caught my eye. Let's see what happens with 19. On 255. So we have y equals 2x minus x squared. We are given x equals 2, and delta x equals negative 0.4. Of course, it's the same with dx. And we're asked to find delta y and also find dy. And then we look at linear approximations. So what is the definition for delta y? Assuming that I call this f of x, what will you say? F of x, since I have delta, I have to write delta x. They are the same, but that's the correct notation. And what is dy? What does dy equal to? We can never forget that. F prime of x, not plus, times. That's it. So please remember these two. That's how we got that relationship, the famous relationship, because they are almost the same. Not the same, almost the same. Okay, so then delta y will be f, how much is 2 minus 0.4, which is 1.6, minus f of 2. And I have to calculate that. dy will be f prime of x. So we find f prime of x to be 2 minus 2x. So this will be 2 times 2 minus 2 times 2. Really? Yeah. Ah, I see. Got carried away. Because it makes no sense. And I said, it doesn't look right. Okay. So 2 minus 4, that makes sense now. Times negative 0.4. So f prime of x is 2. I replaced 2. 2 minus 2 times 2, and dx is negative 0.4. So this is 2 minus 4, which is negative 2, times 0.8. 0.4 is 0.8. Let's see what we get with the exact. 2 times 1.6 minus 1.6 squared minus f of 2, which is, oh, that is okay, 4 minus 4. So let's see how far we are from 0.8. 0.8 is the estimate. And 2, so this is 3.2, and minus 1.6 squared. Oh. I got 0.64. I would say it's pretty close. Yes?
So for dy, is it 2 minus 4 times negative 0.4, or is that?
Yes, because this is this, and this is this.
Oh, that's what. Okay, I didn't put the negative in there. Okay, gotcha.
Better?
Mhm.
Everyone? Any questions? Okay, linear approximations. Before we look at again at our best friend, what do you think this is? It just says that if I have a function at any point where it's differentiable, of course, continuous, it has to be, I can approximate the function with a line. So at any point, so let's go back to our best friend from day one. We have a very strong relationship with this. You can't live without it. Here it is. Of course, f of x. Of course, p. And this time, p has a, f of a. And I claim, and you'll tell me whether you agree with this. Here's my claim. My claim is that not here, not here, not here, but very close to this point, it doesn't matter if I use the function to evaluate or I use the tangent to evaluate. That's my claim. So at any point on the function that is differentiable, I can create a linear function, which is always easier to work with, to estimate close left and right of that point, to estimate the function. Not exact, it's estimate. So let's see how that happens. And again, this triggers series in the next course. Okay. So I'm claiming that only very close. If I want to estimate something here, then I need a new tangent and a new function that is a line. If I want to estimate here, I need a new function that is a line, and I will estimate with that function. But here, I can left and right, if I'm here or very close, I don't need to use the function, and I will use the line to estimate. Now, you can say always, and I'll have to, yes, Eddie, you want to say something? I will say no. If it's a matter of life and death, you may not want to use the approximation or the line, right? Otherwise, you may want to. So let's see how that happens. Can anyone give us the slope of, I didn't mean to write that, the slope of the tangent line at P? Thank you. Can anyone give us the point, the coordinates of point P? A comma f of a, very good. And now I would like y minus y1 equals the slope times x minus x1. I want to determine the equation of the tangent line at P. So here I have P of a. I'm sorry, f of a I meant to write. Here I have f prime of a. And here I have a. Can anyone dictate? Y minus f of a equals f prime of a, x minus a. We agree? Okay, so now this is the y of the tangent. I'm going to move f of a to the other side. This is the line, the equation of the tangent line at P. Therefore, according to my claim from 2 minutes ago, I cannot write that the f of x equals, but I would write that f of x is what? What is the relationship between f of x And f of a plus f prime of a times x minus a. They cannot be equal.
Approximately.
Correct. Yes. This is also called the linearization of f of x near a. Nowhere else, but only near a. Okay, so let's apply this. Find the linearization L of x of the function at a. So the notation of this, not of that, this is the function which is approximately that, is uppercase L of x. Would you like to choose? Find the linearization L of x of the function, doesn't matter which one you pick. Which one? Number one, very good. Number one it is. So this is 1 on 255. So f of x equals x to the fourth plus 3x squared when a equals -1. Let's see again what this means. After we calculate it, we'll talk about it again. So all I have to do is write this. But we know what this is. It's the same thing we looked at a few minutes ago, right? So this is that dx, x minus a. This is the function, and it's that prime. Exactly the same thing. Okay, so I have to find, so x is, this is a function, so x is x. So a here will be -1, a here will be -1, and I have to find f prime of x, which is 4x to the third plus 6x, and I have to plug in -1. So f of -1 is -4 minus 6, -10. How much is f of -1? So it's 1 plus 3, which is 4. I found all the information I needed. So then L of x will be a line, mandatory. F of -1 is 4. F prime of -1 is -10. And then x plus 1. Or L of x, -10x minus 10, but plus 4. It's minus 6. So, remember f of x was x to the fourth plus 3x squared, and a is -1. Let's talk about this one more time. What does it mean? It means that if you decide or you need to evaluate this function very close to -1, like -0.9, like -1.1, there is no need for you to use this. You can use this, which is a linear function. It's not easier to calculate. Now, if you want to estimate this, or I'm sorry, to evaluate this function at -4, you cannot use this line. Because -4 is not close enough to -1. You will get a huge error. Yes, Greg, go ahead.
I just want to make sure. So, for the function, you plugged in -1. You
Yes.
got 4. Then you plugged in -1 for the derivative, and you got 10.
Yes, because I had to fill all those in.
Okay,
I had to
gotcha.
find f of a, which is f of -1. I had to find the prime of -1 and x minus -1.
Okay, gotcha.
So this is the linear approximation of this function near -1. It's a tangent. It's a line. So if you want to evaluate this function at -1.1, you can use the linear function. You'll get a very good approximation.
Gotcha.
But if you want a different number, you have to create a different linear function. So if you want, for example, 5, Then you have to find f of 5, f prime of 5, x minus 5, and you will get a new line, a new linear equation that will estimate near 5.
Gotcha.
Very good. Other questions for me? I would like us to also one more time find the differential of each function. So choose from here. And then we can consider 3.10 finished. I know we have to review it for the test, and we will. At least 2 hours we're going to review. So please choose any function to find its differential. I just want you to remember that the derivative and the differential are not the same. Which one? You mean this one or this? I'm sorry, this one or this one? B or B here? Which one? 11. Very good. Part B?
11 Bravo.
Okay, 11 Bravo it is. So 11b on 255, and we have y equals natural log, the square root of 1 plus t squared. Remember, we are asked to find dy, not y prime. You will see how important this is when we get to chapter 5. That's one of the most important uses of dy. So what would you say? What does this equal to?
That's it. Is that the formula?
So 1 over the square root of 1 plus t squared times 1 over 2 square root of 1 plus t squared times 2t. Okay, till we get used to this, let me just give you an idea. So you have something here, right? You have natural log of something. How do I differentiate something log of a function? It's 1 over this, correct? But then I have to differentiate this because it's not plain x. So that's how I get 1 over 2 the square root of 1 plus t squared. But then I also have to differentiate the inner function, which is 2t. Do we agree?
Yes.
Yes? Okay, so the 2's go away. So I have, I'm sorry, times dt. Be very careful. I got carried away explaining this and that. No excuse whatsoever. So it's the differential, so I have to write times dt. So therefore, dy equals, after I simplify, t dt divided by 1 plus t squared. This is the differential of y. Yes, you can put dt at the top or at the end of the fraction. That's fine too. So you can write dy equals t over 1 plus t squared dt. They are the same. This is a major portion of chapter 5. Any questions? Any questions? Okay, I have roughly about 10 minutes. I will ask you what would you like me to do. We can look at the last section, which is 311, in which I only want you to remember 3 functions. There are 12 functions in there, but I only need 3. Or we can practice some more. Or we can go back to this, if you would like. Would you like to finish up 311 with those 3 functions?
Sure.
Yes.
3 minutes per function.
Okay. No. It's much less than that. So 3.11, the last section of chapter 3, hyperbolic functions. There are 6, and they have inverses, and they have derivatives. So 6 functions with their derivatives and 6 inverse functions with their derivatives. I only request 3. And here they are. Sine hyperbolic x, or hyperbolic sine x. Cosine hyperbolic x, or hyperbolic cosine x. And hyperbolic tangent, or tangent hyperbolic x. Okay, so here's one example that I would like to look at. I did not define them. You don't know anything what they are just yet. I just want to show you a couple of graphs in your book, just these two. And then I'll explain what they equal to, etc., etc., etc. So, you know, a lot of math was developed from needs. So this was one need. When they started transferring the telegraph poles or cables or high power or you name it from point to point, they could not fit a function here. They could not say, okay, what is it? Well, maybe it's a sine, maybe it's a cosine, maybe it's a polynomial function, maybe it's a pure exponential. They couldn't find anything. So here's another one. Ocean waves. They could not really find something that is a good model for ocean waves. So then what they did, especially for this one, which is I think is one of the most interesting ones, which is this case, they put some exponential functions together in a particular order. Of course, they dug deep and they tried all sorts. So they came up with two functions, e to x minus e to negative x over 2 and e to x plus e to negative x over 2. And of course, this one is hyperbolic sine over hyperbolic cosine. So the top and the bottom, the hyperbolic sine, hyperbolic cosine, they're very similar, but one has minus, one has plus. We can find the derivative of all of these three by simply differentiating these functions. So it happens that hyperbolic sine, these are not trig functions. I do not have the answer. I have not researched why they are called hyperbolic. Sine. Hyperbolic is fine, but why sine and why cosine? I guess because the relationships between them are very similar to the relationship between sine, cosine, tangent, etc., etc. That's what I think happened. So this prime is hyperbolic cosine. Hyperbolic cosine, you would expect a negative in there. It's not. It's hyperbolic sine. And of course, hyperbolic tangent, you would expect, and it's true, it's hyperbolic secant squared. That's all I want you to remember. Because everything else, it's in the tables. These are just the basic three functions. If I ask, but I won't. Anything else, I'll give you the formula. Yes, Noah?
The negative for cosine?
No. No. So we have a few minutes if you like. Let's prove that. Not with a definition, I promise. But let's differentiate this. Let's just differentiate. It's a very good question. So e to the x plus e to negative x divided by 2 prime. So this is hyperbolic cosine prime. Of course, I'm not going to mess with the constant. I don't care for it. I'm going to put it outside. E to the x is e to the x. But when I differentiate it, e to negative x, what do I get? And that's why this is hyperbolic sine. we don't have enough time for this problem, but I would like to definitely look at this one with the telephone line, and it has a hyperbolic cosine as expected in it. We can look at that next time. But I would like us to just practice with any problem that has hyperbolic tangent, hyperbolic sine, hyperbolic cosine. Important functions, they have specific applications, and just, which one?
38.
38. Yes, it's a very good one. And then we'll stop. So 38. On page 263 is y equals hyperbolic sine of hyperbolic cosine. Yes, we have to realize that this is the chain rule. It's a function inside another. And what will I have to write? Yes? Of hyperbolic cosine times hyperbolic sine.